All right, let's talk about logistic regression. So last class we had a linear regression refresher, and we covered how to write a linear model in matrix form, and we learned how to minimize the residual sum of squares to calculate beta hat with x transpose x inverse x transpose y. And so linear regression is a great tool when we have a continuous outcome. And we're going to learn some fancy ways to actually do even better in that case in the future. But what about classification problems? So let's revisit some of our classification problem examples. One is we have a qualitative response variable in an unordered set C. And so one example is eye color, for example, like blue, brown, and green. This would be a qualitative response. Or email, for example, spam or not spam. So that response variable y takes on some values in C in this classification problem. And then predictors are a vector x. And so the task is to build a function, some function c of x, that takes x and predicts y. And so this c of x is basically going to be in this set C. The predicted values are going to be in that set. Many times we're actually more interested in probability, so basically the probability that x belongs to each category C, and that's what logistic regression can get us. Okay, so here's an example. We've got some credit card default data. And so here on my x-axis, I have balance. On my y-axis, I have an individual's income. And then I've drawn little x's to indicate if they default or not. So there's a blue x for the folks that do not default on their credit cards, and there's a red x for those that do. And so just looking at this data, we can see that there is probably some relationship between these variables. It looks like people with higher credit card balances are more likely to default, for example. And we can look at that another way. We can look at that with a box plot. And so here I've plotted whether or not they default on the x-axis, either no or yes. And I've plotted the actual distributions here with box plots. And so the folks that are not as likely to default have lower balances compared to those that are. And the income, it looks like, is pretty close, but it looks like those that don't have slightly higher income than those that do default. So if we wanted to try to estimate the probability of defaulting based on these variables, could we use a linear regression? So we could code default as 0 if no and 1 if yes. And then we could fit a linear regression of y on x, and we could classify as yes if y hat is greater than 0.5, for example. And so in this case of a binary outcome, linear regression is actually okay, and it's equivalent to linear discriminant analysis. You can read a little bit more about that in your book if you're interested in it. And so here, the expectation of y given x is equal to the probability that y equals 1 given x. And so it seems like this is a pretty good idea. But the problem is that linear regression can produce probabilities less than 0 or greater than 1, which obviously don't make sense. Because when you're fitting a linear regression model, it's just going to fit a straight line through your data. It doesn't know that you're trying to estimate probabilities. And so you can find space where you end up entering sort of this parameter space that doesn't actually make sense in the context of the problem. And so what could do a better job? Well, probably by the title of this lecture, you know that we're getting at logistic regression, and so that is going to be kind of the better solution here. So linear versus logistic regression. So here, the orange tick marks represent the response, and so either 0 for the folks that do not default, or 1 for the folks that do default. And so on both of these graphs, I'm plotting balance here on the x-axis and the probability of default on the y-axis. And my little ticks are going to be the same in both cases because I'm just plotting those as the actual true y values that we see. But over here, I fit a linear regression model to this data, so I just get a straight line. And so that's going to be able to help me predict, basically, based on this balance, what the probability of default is. But you notice down here, with really low balances, I end up with probabilities less than 0. And as I mentioned, that doesn't make any sense. You can't have a probability less than 0. And so this model is not so great because it sort of predicts outside of the region that we know is realistic. Over here, on the other hand, I'm fitting a logistic regression model. And because the logistic function is a function that is designed for this type of problem where the outcome is bound by 0 and 1, it's got this kind of sigmoid or S shape to it. And so we end up not being able to get values that are less than 0 or greater than 1. And so it's much better for this type of problem. And so over here, where in our linear regression model, we were predicting values less than 1, in the logistic regression setting, it just predicts those as very, very close to 0. So what if we had greater than 2 possible outcomes? For example, if someone comes to the emergency room and we need to classify them according to their symptoms. So for something like 1 if it's a stroke, 2 if it's a drug overdose, or 3 if it's an epileptic seizure. What could go wrong here if I did this with linear regression? So the coding here, when we're doing linear regression, we necessarily have to have linear or numeric values for our outcome. And so our coding 1, 2, 3 implies an ordering, which is not the case in a classification problem. There's no ordering to these. Stroke is not better or worse than a drug overdose, which is not better or worse than an epileptic seizure in this case. These are just different categories. And so by giving them values 1, 2, and 3, I'm implying there's an ordering. And linear regression will treat them as if there is an ordering. And so that's the one problem. And the second problem with this is that the coding also implies equal spacing. And so that means that the difference between a stroke and a drug overdose is the same as a drug overdose and an epileptic seizure. And that also is not a good assumption for this classification problem. So there are two problems with trying to use linear regression when you have more than 2 classification classes in a classification problem. The first being that it implies an ordering, and the second being that it implies the spacing depending on how you've picked those values. So linear regression is not appropriate here under any circumstances. In this case, you want to do something either multi-class logistic regression or a discriminant analysis. Okay, so let's get into what logistic regression actually is. And so just to note here, when I'm writing P of x, this is shorthand for the probability that y equals 1 given x. And so this is shorthand that you'll see maybe in your book too. But this is what I mean. I mean the probability that y equals 1 given x. And so that probability is equal to e to the beta 0 plus beta 1x over 1 plus e to the beta 0 plus beta 1x. And so no matter what values beta 0, beta 1, or x take on, this probability, the probability that y equals 1 given x, is always going to be between 0 and 1 based on the way that the logistic function works. And you can try that yourself if you'd like to plug in various values here to see if you can ever get it to break, and you can't. So there you have it. So it turns out we can rearrange this into the following form. And so if I take the log of that px over 1 minus px, then I end up with beta 0 plus beta 1x. And so this gets it back into that linear form that we expect. And so what do you think this transformation is called? This is called a log odds or logit transformation of that probability of y equals 1 given x, or the p of x. So logistic regression ensures that our estimates for p of x, or this probability of default in this case, are between 0 and 1. So this is excellent. It's what we're hoping for. Okay, so refresher, how did we estimate beta hat in linear regression? Well, we just did this in the last class. We used that minimized the residual sum of squares. And so in logistic regression, we're going to use something else. We use something called maximum likelihood to estimate the parameters. And it turns out, actually, we could use maximum likelihood for linear regression as well. It's just that it's such a nice, easy solution to just minimize the residual sum of squares that that's often how we focus on it for linear regression. But for logistic, we can use this maximum likelihood approach to estimate those parameters. And so this likelihood is equal to this symbol here. This is a multiplication symbol. And so we multiply that p of xi, where y equals 1, and then 1 minus p of xi, where y equals 0. So this likelihood, it gives the probability of the observed 1s or 0s in the data. And we pick a beta 0 and a beta 1 that maximize this likelihood. And we're going to let R do the heavy lifting here, so you don't have to worry about kind of doing this by hand or anything. Okay, so this is how we do this in R. So now, instead of using the linear underscore reg function, we're going to use the logistic underscore reg function. And instead of using the LM function, we're using the GLM function. And that's because GLM stands for generalized linear model. And so logistic regression is actually a generalized linear model. And so that's why we're using this engine. So we plug in logistic underscore reg, we pipe that into the GLM engine. And then the rest of this should look just like we've expected, just like we've seen in the previous examples. And so we still use that fit function. We have our y here is default, x is balance, we set our data, and if we pipe that to the tidy function, we get this nice output where we can see our estimates here. So this is our beta hat estimate for the intercept, negative 10.7, and the beta hat estimate for the slope, or for balance, 0.0055. We get our standard errors, our t-statistics, and our p-values. Okay, so let's make some predictions now. What is our estimated probability of default for someone with a balance of $1,000? So using that formula that we had shown on the previous slide, we want to take e to the beta hat 0 plus beta hat 1x over 1 plus e to the beta hat 0 plus beta hat 1x. And so in this case, beta hat 0 is negative 10.65. Beta hat 1 is 0.0055, and x for this predicted, we want to know a balance of $1,000, and so that's what we're going to plug in for x. So we'll do the same in the denominator here, and we end up with 0.006. Now what if we wanted to go up to $2,000? And so if we wanted to change to predict the probability of default for someone with a balance of $2,000, instead of plugging in 1,000 here for x, we would plug in 2,000, and we end up with 0.586. So the probability of default for someone with a balance of $2,000 is 0.586. Now I'm going to refit this model to predict the probability of default given that the customer is a student. So the probability of default, the default equals yes, given student equals yes, and I'm going to plug this into that same formula, but now my x is just going to be 1, because when we're dealing with binary variables or variables like, with just 2 levels, like student, for example, it's going to, the way that the model is fit, this is probably a refresher maybe from 212 or a previous statistics class, but the way that the model is fit, it's going to be, it's going to set this value to 1 when yes, or 0 when no. And so I can just plug in a 1 there for the x value, and I see that the probability of default given the customer is a student is 0.0431. Now how would this change if student equals no? So if I wanted the probability that default equals yes given student equals no, what do you think would change? So if I want the probability that default equals yes given student equals no, then I would change my x to be 0. And so that's going to just cross this whole part out. And because this model only has 1 variable in it, when I'm at the referent category for that variable, then I end up with just the intercept. And so I just would have this e to the negative 3.5041 divided by 1 plus e to the negative 5.041. So I end up with 0.0292. So the probability of defaulting given the customer is not a student is 0.0292. So it turns out this same model can be used for multiple logistic regression. And so when you have more than just one predictor, and it comes out to be very, very similar. So in the logit or that log odds form, in the linear form, we have the beta 0 plus beta 1x all the way up to beta p xp, and so this should look pretty familiar. And similarly, when we're in the probability form, we end up with e to the beta 0 plus beta 1 x1 plus beta 2 x2 all the way up to beta p xp. And the denominator does the same. We've got 1 plus e to the beta 0 plus beta 1 x1, etc. So here's an example where instead of just looking at one variable, I'm going to look at three. And so I'm looking at balance, income, and whether the customer is a student. And I'm still predicting whether or not they default. And so notice here, let's go back a page and just take a look at that coefficient. That coefficient for beta hat 1 or for student was 0.404. But once I do multiple regression, once I add in balance and income, now that its coefficient is negative 0.64. And so why do you think the coefficient for student is negative now when it was positive before? And so this is a concept known as confounding. And so what's going on here? Well, if we look at credit card balance and default rate, on this plot, I'm basically showing you kind of two different models. On the dashed line, I'm showing you the first model I fit that only included information about whether the customer was a student. And so the blue represents those that are not students, and the orange represents those that are students. And so if I look at the difference between those two dashed lines, it looks like students in the orange are more likely to default than non-students. Their default rate is higher. The orange line is above that dashed blue line. So when I look at it in the univariate sense or with just the one variable, that's what I see. But if I plot credit card balance and I look at the default rate split or stratified by student here, and so on the orange, I have my students equal yes, and in the blue, I have students equal no. And now I see a very different story. The order of those lines are flipped. And so now when I look at this, the orange line is always below the blue line. And so that looks like once we take into account credit card balance, students are actually less likely to default than non-students. And so we can then look at basically what's going on here, that we know that credit card balance is a good predictor for default rate from the previous slides. We saw that people with higher credit card balance were more likely to default. And looking at this box plot, we also are seeing that students are more likely to have a higher credit card balance. And so when we only look at student status in a model and we don't account for credit card balance, it looks like students are more likely to default. But that's actually not necessarily just because they're students. It's looking like that because we are actually sort of accounting a little bit for the credit card balance in that variable. And so we need to account for that in the model or fit that multiple linear regression model that accounts for balance so that we can take out that balance effect and be able to examine just the student effect alone on defaulting. So to say that in sort of statistical terms, students tend to have higher balances than non-students, which means their marginal default rate is higher. And so that's the marginal default rate is going to be the marginal effect is that model that only included students in it. That's why this dashed line here for orange is above the dashed line for blue. But for each level of balance, the student default is less. And so that means their conditional default rate is actually lower. So conditioning on balance, our student default rate is lower than our non-student default rate. And so far, this is an important concept and one that I want to make sure that you sort of settle in with, because this concept of confounding is really important, especially when we're trying to draw inference or understand how variables impact the models. And we're going over it now because I'm sort of building up on this, but this is also just as much a problem with linear regression as it is with logistic regression. Okay, so far we've discussed binary outcome data, but we can actually generalize this to situations with multiple classes. And so here I have a linear function for each of the k classes, and this is known as multinomial logistic regression. And so this is how you could generalize logistic regression to be more than just for a y variable that's binary or just 0, 1. You could have multiple classes there.